My dear students, welcome to Department of Chemistry, JCBMC College SRINGERI. See, in my last video class, we have seen some of the important concepts of thermodynamics. So, what are the things that we have seen in my last class is thermodynamics, definition of thermodynamics, open system, closed system, isolated system, and different processes like the isothermal process, isobaric process, isochoric process, intensive property, extensive property. So, all these things we have seen. So, just we will recap some of the terms that is used in our last video lecture. So, we have seen system. What is meant by system? System means any specified portion of the matter under thermodynamic study which is separated from the rest of the universe with a definite boundary. For example, in a beaker, you take little water, it constitutes a system. The space around the beaker, air, so that is known as surrounding. So, surrounding means, so excluding the system, so which can exchange both energy and matter with the system. So, that is known as surrounding. So, the glass, the wall of the glass beaker which constitutes a boundary. Okay. So, next we have seen open system. What is meant by open system? Open system means which can exchange both energy and matter with the surrounding. So, that is known as open system. So, closed system means, so which can exchange energy but not matter with the surrounding. So, that is known as closed system. So, next we have seen isolated system. Isolated system means which cannot the exchange both energy and matter with the surrounding. So, that is known as isolated system. For example, the coffee in a thermos flask, it is an example for isolated system. So, next we have seen the different processes. So, what are the different processes we have seen? Isothermal process, a process which takes place at constant temperature. So, that is known as isothermal process. Then a process isothermal, then adiabatic process. So, in this case no heat is exchanged between the system and the surrounding. So, that is known as adiabatic process. So, then we have seen the isobaric process. Isobaric means the process in which the pressure remains constant. So, that is known as isobaric process. Then we have seen isochoric. Isochoric means the process in which the volume remains constant, right. So, next we have seen cyclic process. Cyclic process means which undergoes a process which undergoes a different stages and reaches the initial stage. So, that is known as cyclic process. Next we have seen reversible process. What is meant by reversible process? A process which can be reversed by changing the driving force by infinitesimal amount in the opposite direction. So, that is known as reversible process which can be reversed at any instant. Okay. So, next irreversible process. Irreversible process means which cannot be reversed by any instant by changing the driving force in the opposite direction. All natural processes are irreversible process. So, next we have seen the properties. So, intensive property and extensive property. So, what is meant by intensive property? Intensive property means property which does not depend upon the quantity of matter. So, that is known as intensive property. For example, we have seen temperature. So, temperature is an intensive property. Next, extensive property. Extensive property means which depends upon the quantity of matter. So, that is known as the extensive property. For example, volume. Volume is an extensive property, right. So, these are all the things that we have seen in our first video lecture. So, today we will see some important derivation. So, that is expression for work done during isothermal expansion of an ideal gas. So, before that, see here when the pressure is different, the system and the surrounding pressure is different. So, then what happens we can say, suppose you take the pressure is different. So, here the pressure of the system and the surrounding which is different. So, then the energy is transformed in the form of work. For example, if the pressure of the gas here, the ideal gas, the pressure of the gas is more, here the pressure of the gas is more than the pressure of the surrounding. So, then the gas expands, okay, the gas expands. So, then the work is done work is done by the system on the surrounding. On the other hand, if the pressure of the surrounding is less, more pressure of the surrounding is more, so then work is done on the system. So contraction takes place. In the earlier case, the expansion takes place. Okay, in both the case, during the contraction or expansion, the work is done on the system or work is done by the system. So during both the cases, the mechanical work is done. Okay, so here the work is equal to P delta V. Okay, so work is equal to P delta V. So work is done equal to P delta V. So work is equal to minus P delta V, or work done is equal to plus delta V. Okay, in this case work is done by the system, here work is done on the system. So here W is equal to positive, work is done on the system, here work is done by the system. Okay, so let us see the expression for work done during isothermal expansion of an ideal gas. So for example, consider an ideal gas enclosed in a cylinder which is fitted with a weightless, frictionless, movable piston. Suppose if it expands from volume V1 to V2, then pressure decreases from P1 to P2 successively. The pressure of the gas, let the pressure of the gas equal to P. Suppose if it expands from volume V1 to volume, so this is initial position of the piston, so this is final position of the piston. Okay, so here volume V1 to V2, then the pressure decreases from P1 to P2 and the distance travelled by the piston equal to dl. So for all practical purpose, so here the P external equal to pressure of the gas. Okay, here the external pressure is decreased by a infinitesimal amount, very small amount dP, then the gas expands. Okay, so for practical purpose, P external pressure is equal to pressure of the gas, right? The work done during this, you can write, say work done during this expansion, so W is equal to here minus P delta V. Okay, so minus P delta V. So how this W is equal to work done is equal to minus P delta V? We know that the force is equal to here the work is equal to, okay, force into displacement. Force into displacement. Okay, right. So here pressure is equal to, work is equal to force into displacement. So you know that pressure is equal to force by area, force by area F by A, or pressure is equal to force by area therefore W is equal to force into displacement. So that is equal to pressure into area into displacement. So that is equal to P into A into dl. So that is displacement is equal to dl. So here, so that is equal to P into delta V, where A is equal to area of cross-sectional area of the piston. So dl is equal to distance travelled by the piston. So therefore equal to P into delta V. So this is delta V is equal to change in volume. So here the work is done by the system. So therefore W is equal to minus P delta V. So then the total work done during this isothermal expansion of an ideal gas, when the pressure changes from P1 to P2 and volume changes from V1 to V2 at constant temperature, is given by, so W is equal to, here W is equal to minus P delta V. You know that PV is equal, from ideal gas equation, PV is equal to nRT. So you can substitute here. So here P is equal to, here you can substitute P equal to nRT by V. So therefore, so the W is equal to minus integration V1 to V2 volume nRT into dV by V, right. So then here W is equal to V1 to V2 nRT by dV by V. Taking integration, W is equal to minus nRT integration between the limit V1 to V2 dV by V. So that is equal to W is equal to minus nRT ln V2 by V1. So that is W is equal to here ln means log to the base e, which is converted into log to the base 10. So by multiplying 2.303. So therefore W is equal to here W is equal to minus 2.303 nRT log to the base 10 V2 by V1, right. So at constant temperature P1 V1 equal to P2 V2 or V2 by V1 equal to P1 by P2, substituting this one in this equation. So you will get W is equal to minus 2.303 nRT log to the base 10 P1 by P2. So these two expression. So when the volume is given, so work done can be calculated by using this expression. When the pressure is given, so the pressure is given, work is done, which is calculated by using this expression. So W is equal to minus 2.303 nRT log V2 by V1. And W is equal to minus 2.303 nRT log to the base 10 P1 by P2. So these two are expression for work done during isothermal expansion of an ideal gas. So let us see one or two problems. So here W is equal to minus 2.303 nRT log to the base 10 V2 by V1. When volume is given, so you can use this formula. For example, here calculate the work done when 2 moles of an ideal gas expands reversibly from a volume of 10 to the power of minus 3 cubic meter to a volume of 10 to the power of minus 2 cubic meter at 290 Kelvin. So given R is equal to 8.314 joule per Kelvin per mole. So substituting what is given here. So first you have to write the data. So here V1 is equal to 10 to the power of minus 3 cubic meter, V2 equal to 10 to the power of minus 2 cubic meter, temperature T is equal to 290 Kelvin and N is equal to number of moles equal to 2 moles. Substituting these values in the expression 1. So that is W is equal to minus 2.303 nRT log to the base 10 V2 by V1. So substituting here W is equal to minus 2.303 into 2 into 8.314 into 290 into log 10 to the power of minus 2 divided by log 10 to the power of minus 3. Okay, so simplification, on simplification you will get W is equal to minus 1105.34 joule, or in terms of kilojoule you can write. So here 11.105 kilojoule. Okay, right. So then when the volume pressure is given, so then we can use this expression. So W is equal to minus 2.303 nRT log to the base 10 P1 by P2. So here you can see the problem 2. Here calculate the work done when 1 mole of an ideal gas expands isothermally and reversibly from a pressure of 100 kilo Newton meter minus 2 to 20 kilo Newton meter minus 2 at 300 Kelvin. So, what is given here? So, here the N is given, N is equal to 1 mole, then temperature is given, temperature T is equal to 300 Kelvin, and the pressure is given, P1 is equal to 100, here 100 kilo Newton meter minus 2, and P2 is equal to 20 kilo Newton meter minus 2, right. So, when you substituting these two values in this expression, see here W is equal to minus 2.303, N is equal to here, N is equal to 1, and R is equal to 8 point gas constant, R is equal to 8.314 into T, temperature is equal to 300 Kelvin log to the base 10. So, P1 is equal to 100 kilo Newton meter minus 2, P2 is equal to 20 kilo Newton meter minus 2. On substituting and simplification, you will get W is equal to minus 4015.16 joule, or in terms of kilojoule you can write, so here minus 4.015 kilojoule. Thank you, my dear students. So, remaining things we will see in the next class.